Okay, so polar and non-polar covalent bonding. Okay, so Nat5 recap before. What are bonds? Okay, so bonds are electrostatic forces of attraction which hold atoms together. Okay, the type of bond formed depends on what elements are bonding, so what elements are involved. And from National 5, the types of bonding you know are covalent, so you get covalent molecular and covalent network. Okay, you know ionic and you know metallic. Okay, so today we're going to be adding on to this knowledge. Okay, so we're going to be building on it. There's a little bit extra that what you need to know at higher than you do at National 5. Okay, so covalent bonding then. From National 5, you know that a covalent bond is an electrostatic force of attraction between positive nuclei and negatively charged outer electrons. So remember, it's a shared pair of electrons. Your positive nucleus, your protons in there, are attracted to the negative electrons that they are sharing between the atoms. Okay, so covalent bonds are formed between non-metal atoms, and that's important. They're always non-metal. Okay, and examples of this is your diatomics. Okay, so your H nothing down, that's a way to describe it. But there's 7 diatomics you need to know, and it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There's different ways of remembering it. The one I like to use is H nothing down. Okay. So, when we're looking at, for example, fluorine that have got bonded together. So we've got the electrons of one fluorine atom in the pink and one in the blue. And you can see that in here is your shared pair of electrons. Okay, so the outer shells are sharing one from each so that they become stable. They are bonded together. This in the middle here, your shared pair, is your covalent bond. Okay, so adding into your higher now, so using knowledge that you've already learned, each atom has the same electron negativity value. Okay, so your fluorine atom has an electron negativity value of 4.0. Okay, so that means both of these are 4.0. When they are both the same, this means your electrons are going to be shared equally in the bond because you have equal pull from each atom. Okay, so your electrons are going to be situated in the middle. Yes, so when the electrons are equally shared, this is known as a non-polar bond. Okay, a non-polar covalent bond, it can also be known as a pure covalent bond. So you might see both of them in questions. Okay, so non-polar bonding is when the atoms involved have no difference in electron negativity. Okay, this means the electrons are shared equally, and in questions it's usually asked about diatomics. Okay, so they both have the same pull of these shared electrons in the bond, so your electrons are right in the middle. They're shared and pulled equally, which means they're going to be in the centre of the bond. Okay, so what happens when they have different electron negativities? Okay, so when the atoms involved in the bonding contain different electron negativities, they are known as polar covalent. So now we've had non-polar, shared equally, no difference in electron negativity, and we have polar, which has a difference in electron negativity. Okay, so this difference in electron negativity, remember, it means that one of the atoms is pulling the electrons closer to itself, which means the electrons are shared unequally in the bond. Okay, so that means that the atom that has a larger electron negativity is going to pull the electrons closer to itself. So example, HF, fluorine and hydrogen. Hydrogen is 2.2, fluorine is 4, so your electrons are going to be pulled closer to the fluorine because this has a higher value. Okay, so with your electrons getting pulled closer to the fluorine, okay, you have this uneven share of electrons. Okay, this causes the bond to be partially charged. So part of the bond is going to be positively charged and part of the bond is going to be negatively charged. Okay, we show this partial charge as delta. Okay, so the delta looks like that. So with your fluorine, we'll keep the same example going all the way through. So your fluorine is pulling electrons closer to itself. That has a higher electron negativity. Okay, so this is going to become partially negative because the electrons are closer to the fluorine. Okay, remember your electrons are negatively charged, which is why it is going to be partially negative. Your fluorine is pulling the negative charges towards itself. Okay, so it's going to be delta negative here. Yes, so your fluorine has a bigger pull in the electrons. It's pulling these negative charges towards it, which is causing itself to be partially negative, which is also known as delta negative. So in a bond, because now your fluorine is partially negative, okay, your H atom becomes partially positive. Because remember, it's a shared pair of electrons. They both have a certain pull on these electrons that they're sharing, but just fluorine is pulling them closer to itself. So your hydrogen is partially positive. Okay? You can never have a bond that is partially negative at both sides. Okay? So they need to counteract each other. So if you've got a partially negative side, you need a partially positive side. Okay? It must be equal. So, going on to this, so you've now had your polar bonds, which is your difference in electron negativity values, and you've got your non-polar bonds, which is no difference in electron negativity values. Okay, and although a compound may contain polar bonds, overall it may be non-polar. Okay, this is due to the shape of the compound. Okay, so if it has a symmetrical structure, like your carbon dioxide here, your partial charges are pulled in opposite directions. Okay, so basically the electrons are being pulled equally in opposite directions because here your oxygen has a higher electron negativity than carbon, so the same at both sides. So these electrons are being pulled out like this, okay, and as a whole it will cancel out the polarity, okay, because they're getting pulled separate ways. Your electrons from your carbon are getting pulled equally this way as they are getting pulled equally this way. Okay, so when you have polar bonds and a non-polar molecule, your molecule must be symmetrical. Okay, it must have all the same types of bonds in it, and they all must be in a symmetrical formation. Another example of this is a tetrahedral structure. Okay, for example, your CF4. Each carbon to fluorine bond is polar because your carbon is 2.5 and your fluorine is 4.0. Okay, but these electrons, all the 4 pairs of them, are getting pulled towards the fluorine in equally in opposite directions. Okay, so because overall the molecule is symmetrical, the molecule will become non-polar. So it is possible to have polar bonds but non-polar molecules. Okay, and the last little bit of this video then is what happens if it's not symmetrical. What happens if you have a polar bond but you don't have a symmetrical molecule? What happens then? Okay, so when you have a polar bond, okay, and you do not have a non-polar molecule, if it's not symmetrical, okay, so when the atoms have a difference in electron negativity and they're not symmetrical, they're not getting pulled equal ways, the molecule is said to have a permanent dipole. Okay, so a dipole is when each side has a different charge, each end has a different charge. Okay, so for example, your water, H2O. This is the shape of water. It's an angular molecule. I'll just write that down. Okay. Your oxygen has a higher electron negativity value than your hydrogen. So your oxygen pulls the electrons closer to itself and it becomes partially negative. Okay. This molecule is not symmetrical. They don't get pulled out each side because your oxygen has two sets of lone pairs here, which prevents that. Okay, so your hydrogens stay down here, which means your electrons are being pulled closer to the top and it's not symmetrical, so you're going to have this permanent dipole. Your oxygen is always going to be partially negative and your hydrogens are always going to be partially positive. Okay.